Welcome, everybody, and welcome to this seminar, online seminar of the low altitude ionospheric physics working group of the AOGS Regional Advisory Committee. We have been organized such a seminars for I think the third time now, and today's talk it will be given by Ms. Syukriah Khamdan. And she is very young, as you can see, you will see, and she's currently a PhD student at the Universiti Teknologi Malaysia. Before joining the University Teknologi Malaysia, she received her bachelor degree of engineering in geomatics in 2014. And then she went to the, I think, the same university, I suppose, to receive her master's degree and working on geometric engineering in 2019. And now she is in the group working on geometric innovation research group with the Professor Alvin Musa is the leader of the group, and her work, her research work, is focused on the GPS ionospheric studies and tomography, ionospheric tomography. That is, and as she will explain to you, I think she published a couple papers already in, I think in JGR or some other journals. And she's going to report to you her recent work in this field. And Syukriah, please, it's all yours now.
All right, okay. Thank you, Professor Ed. Okay, very good afternoon to everyone. My name is Siti Syukriah binti Khamdan. I am from University Teknologi Malaysia under Geometric Innovation Research Group. I am a PhD student. So today I would like to share with all of you some of my previous work on the mapping equatorial ionospheric profiles over Peninsular Malaysia by using the GPS tomography. Okay, so roughly this is my presentation outline. Okay, okay, so for the overview, the first part is on the ionosphere layer. So as all of we know that the ionosphere lies at the upper region of the atmosphere, approximately within 70 to 1,000 kilometers above the Earth's surface. And it consists of free electron and ions that are controlled by the gravity and magnetic fields of the Earth. So the ionosphere consists of a different layer, which is D layer, E layer, and also F layer that exists during the daytime and also the nighttime. And the ionosphere layer and the ionosphere also can be divided into three main regions based on the location, which is the high latitude, known as the aura region also, and mid latitude, which is around plus minus 20 to 60 degrees of the geomagnetic equator, and also the equatorial latitude or low latitude region, which is around plus minus 20 degrees of the geomagnetic equator. So over this equatorial region, actually, we have unique conditions of the ionosphere because due to the magnetic fields that is nearly parallel to the Earth's surface. And there are numbers actually of the ionospheric irregularities that also have been reported that occurs around this region, which is EEJ, we have the plasma bubble EPB, we have the spread F, we have the EIA, and also others. And then this region also contribute to the global maximum of electron density with time delay scintillations and also the large gradient in spatial distributions of the electron densities. So other than that, for the ionospheric studies, for a decade, we have used GPS as tools to observe and monitor the ionosphere. So we have a dense network over the world. For example, we have the IGS, we have UREF. For the local network, we have the Malaysian real-time kinematic network. And also we have, other than that, we have the National Research and Development Cost Network. They're also located over the Malaysia. That allow us for observe the ionospheric estimations and monitoring for the local and global scales. And beside then using the GPS, we also have the ionozone, magnetometer, air glow, and scatter radar, where all of those instruments actually compared to GPS, they have a high maintenance cost, and its functionality may cause to the large data gap. So by using the GPS, the estimation we will use to using the total electron content, TEC, and we present it in two-dimensional by adopting a single layer model, where this model assumes the ionosphere is compressed to a thin shell within the height of the 300 kilometer to 450 kilometer, where we assume that this height has the highest variability of the free electron, and it gives the largest effects on the GPS signals. However, the problem is the single layer model neglect the vertical information, and it has the limit the GPS capability to map the vertical structure of the ionosphere. So the motivations of this study, actually, we have 5 main, which is the first one is on the ionospheric global model. So we have the existing global model. For example, we have the ERI and also the NIQUIC model, which is based on the worldwide data measurement. And for sure, it has best described the global conditions of the ionosphere. However, in Malaysia, during the study period, or my study period, there are no in-situ measurements that contributed to the development of the both model. Hence, the model is based on the interpolation data, and it is less accurate to describe the local ionospheric condition. And the second one on the unique ionospheric conditions over the equator region. As I have mentioned before, there are many occurrences of ionospheric irregularities. And Malaysia, it is located around the near magnetic equator, and the ionospheric condition profoundly severe because of the occurrences of ionospheric irregularities, and also known as the highest value of electron content, and has a large gradient in spatial distributions of electron density. And the conditions of ionosphere in this region also highly affected by the sunspot, time of day, time of year, and also level of the solar activity. On the third part is on the classical technique measurements, where in Malaysia we have, other than GPS, we have the magnetometer and ionozone. We have one ionozone station located at the Universiti Tun Hussein On. Okay, this instrument actually have the limit spatial and temporal coverage, and also high maintenance cost, where the dysfunctionality has a large data gap and limit the ability for continuous ionospheric studies. And the fourth one is the limitations of the single layer model, where, as I mentioned, it only focuses on the certain height, which is the altitude of the maximum density of electron, around 350 to 450 kilometer, and which is only focused at the F region only. And it limits the ability to obtain the variations of ionosphere over D and also E region. Therefore, when we are using this model, we cannot obtain the ionospheric profile will remain unknown. And the last part is on the reconstructions of the inversion models. So when we are using the GPS to reconstruct the three-dimensional ionospheric model, we will use the slant TEC data, which is provided by GPS measurement. So while during the reconstructions of ionospheric tomography, the computation may face an ill-conditioned matrices. Therefore, we will need to find a suitable inversion model, which is required for the reconstruction electron density profile of ionosphere. And this also because we are also involved with the large amount of the slant TEC data during the inversion process. Therefore, the three-dimensional ionospheric electron density profile is reconstructed by using the tomography method, which only will be covered over the Peninsular Malaysia. So in doing so, there are 3 main steps that will be followed, which is the first one, we will study the variations of the ionosphere over the study area. And the second part, we develop the tomography module. And the last part, where we focus on the selected case study in order to observe the capability of the modules in the detections of ionospheric irregularities over the study area. So the methodology in this study divided into 5 main phases, which is the phase 1 on the planning and design and then data acquisitions. The third phase, TEC estimations and analysis. The fourth phase will be development of GPS tomography. And the last part is on the summary and also the recommendation. So to go through on the results actually for the ionospheric TEC trend analysis. Okay, So in this part, we will use the GPS network over the Malaysian region, which is Malaysian Real-Time Kinematic Network that have been managed by the Department of the Survey and Mapping Malaysia. So we will use the 6 years observation data from the year 2009 to 2014. And by using the 30-second interval data, so all of the MyRTConnect station total is around 78 stations. So by using the Bernie software and then version 5.0, we will produce the TEC based on the spatial resolutions, 1 degree to 1 degree in latitude and longitude with the 1 hour temporal resolution. So this is roughly the estimation of the slant TEC, and also we obtain the vertical TEC by using this equation. Okay, so this is roughly, and the table shows the processing parameter and processing strategy that have been used in the Bernie software, where we are focused on the height on the 400 kilometer, and the TEC will be generated for 1 hour. So here we will see the mean TEC variation. On this figure, the first figure is the daily mean TEC over Malaysia versus daily sunspot number from the year 2009 to 2014. And then on the side is on the minimum yearly TEC, average yearly TEC, and maximum yearly TEC, which is plotted together with the yearly mean solar flare index. So based on these two figures, the findings can be found is the daily mean TEC increases with the increasing number of the sunspot, where it illustrates the relationship of the sunspot number that affects the conditions of the ionosphere. And also, it also shows that the trends of the TEC variation, which is related to the ascending and also descending phases of the solar cycle, wherein during the study period is around during the solar cycle 24. And then for the map here is actually the mean TEC over Malaysia from year 2009 until 2014, where we can see that the spatial variation is increased together with the longitudinal and decrease in latitudinal direction, which is similar to the trend that shown by Leong in the investigation over the same study area during the solar cycle 23. So on the next part is on the temporal variations of the TEC. We can see here is the plot of the plot on the yearly based on the time UT versus with the time in a month, and from year 2009 until 2014, and beside is on the dyno variations for the months from the January until December for during the study period. So from the result, we can see that the maximum TEC is actually occurs during 08 UT and minimum during the 21 UT, where the maximum and the minimum actually are related with the production rate of the ionizations. And we can also see that actually the TEC achieve maximum during the equinoxes, where especially during the March equinox, and minimum during the solstice, especially during the July solstice. And this is because the thermospheric circulation between the northern and southern hemisphere weaken and increase the TEC value during the equinox, and the motions of the neutral wind from summer to winter hemisphere weaken the ionization crest value during solstice, and it decreased the TEC value. And the result also shows the equinoctial asymmetry, where we can see the vernal equinox is higher compared to the autumnal equinox. However, I would like to highlight on the year 2011, where we found that during that year, the TEC actually found higher during the autumnal equinox, where we assume that this is maybe due to the thermospheric neutral wind and also the solar UV flux as a main factor of the increasing TEC during that period. So as we seen at the OPNIL web NASA, and then we found that the mean value of the solar flux for the year 2011 during the autumnal equinox is much higher, which is around 140.67 compared to the vernal equinox, which is around 108.62, which explains why during the autumnal equinox is higher compared to vernal equinox during the year 2011. And on the next part is on the development of the tomography modules. So in the development of the tomography modules, we have to taking care of a few parameters. For example, for one of it is a differential code bias. So on the differential code bias actually is the interfrequency bias, which is exists in the TEC estimation from the GPS measurement as shown in this equation. So it consists of the receiver and also the satellite code bias, where both estimation are based on the satellite and receiver type of observation, it's the satellite characteristic, and also the receiver and satellite hardware. So why this code bias is very important? Because the first one is the line of sight TEC from the GPS measurement are corrupted with this bias. And it is very difficult to estimate TEC value if we neglect the DCB. And different satellite and receiver have a different DCB values, and the error in DCB estimation may lead to the negative or wrong estimation of the TEC value, which also can degrade the GPS accuracy and the precision. So there are numbers of agencies have been estimated the differential code bias for the receiver especially. For example, we have the JPL, we have CODE, we have also IGS. However, they are only estimate the receiver code bias only for the station that have been managed. So in order to determine the receiver code bias, there are a number of approach can be used. For example, we have least square estimation, minimizing standard deviation, singular value decompositions, and also satellite receiver geometry changes. So in this study, we focus on the first two approach, which is least square estimation, where we'll use the Bernice software. And the second part is the minimizing standard deviation, where we'll adopt algorithm from the Ionolog bias that have been introduced by Arikan. And further explanations on the equations and also about the Ionolog bias and also the Bernice software approach can be referred to this paper, which is about on the estimation receiver code bias for my Etiquette station. So on the result, for the first part is we do an assessment of receiver code bias with the IGS station. So the assessment to the period is around 181 days during the year 2010 from the 1st January to the 30th June of 2010 with the 30-second data intervals. So the receiver code bias from the Bernice and also Ionolog will be do assessment together with the IONEX from IGS Analysis Center. So in doing so, we choose 4 stations from the IGS, which is Coco, Darwin, Hyde, and NTUS. So here is the location of the station, IGS station. So on the bar chart here is we can see the estimation of mean receiver code bias, where the blue bar shows the Bernice, green show the IGS, and the red show the Ionolog. So roughly we can see here that the differences between receiver code bias from Bernice and also Ionolog we can see are within around 0.1 to 1.0 nanosecond. So in order for further analysis, we observe the residual, which is can be calculated from this equation, which is Bernice compared with the IGS and also Ionolog compared with the IGS. So here the result is we can see that on the graph is on the R square the graph shows the Bernice and Ionolog versus with the IGS, where on the left part graph is on the station for the Bernice versus with the IGS. Meanwhile, for the right part is the Ionolog versus with the IGS for the 4 station for IGS station, Coco, Darwin, Hyde, and NTUS. So overall, we can see that the Bernice and Ionolog method can seem to have a good agreement with the estimation from the IGS Analysis Center, where the R2 value from the Ionolog method is around 0.6 to 0.9 nanosecond, and which is more consistent with compared to the Bernice, which is around 0.3 to 0.7 nanosecond only. So from here, we can see that we like to highlight for the station Coco, we can see that the R2 value is very lower compared to another stations. And from the table here also shows that the Coco has the largest residual value, where we can see is around negative 0.6 from the Bernice and also 0.76 from the Ionolog compared with the other station. So based on the Arikan, exact for the same station, Coco, in their study, they also presented, found that there are largest difference for the station Coco, where the values are up to 2.35 nanosecond. So based on the analysis of the differences, because maybe due to the receiver firmware or type of the receiver that contributed to the largest mean residual of the RCD for the Coco station. So during the study period, based on the IGS Analysis Center on the log file, the firmware for the rest of the 3 selected IGS station, which is Hyde, Darwin and also NTS actually very up to date compared to the COCO station. So this may be because, and then during the study period also, we found that for the COCO station have a different receiver type compared with the other station where COCO used the Trimble and R5, and meanwhile for the another station using the Leica. However, further investigation on this is required because we would like to see whether the receiver firmware and type of the receiver are very have the effect on the receiver code bias values. So on the next part is on the assessment for the MyRT station, where we can see all of the 78 stations using the similar period during for 181 days from 1st until 30th June 2010 that covered for the Malaysian region. So we can see overall that there are small or least differences between of the receiver code bias between both methods. And then we can see that the T station has the largest value of the mean receiver bias. Meanwhile, Tene station has the smallest value of the mean receiver bias. And then we can see that the receiver code bias from the INOLAB is much more smaller compared from the Bernese. So we can see here on the second part is on the latitudinal dependency of the receiver code bias. Okay, 99% actually for the standard deviations of the receiver code bias actually less than 1 nanosecond for both methods. Meanwhile, for below than 0.5 nanosecond, 63% from the INOLAB and 47% of the standard deviations of receiver code bias from the Bernese square. So, and then we found that Segi station actually has the highest value of the standard deviation for the receiver code bias for both methods. And then this is because we found that because they are due to the lack of observation during the study period compared to the other station. And then we found that from the result also there are no latitudinal dependency that has been observed for MyRT station since there are no systematic trend were found. And similar to the Ma and Maruyama in their study, they are also found no latitudinal dependency of the receiver code bias for GPS network over the Japan area. And then based on this assessment, we found that the INOLAB bias, we use the algorithm, the adapter algorithm for the INOLAB bias actually suitable to be used to estimate the daily receiver code bias so that we can use this method for the development of the ionospheric tomography module. So on the next part is on the development GPS tomography module itself. So GPS ionospheric tomography actually is a method to reconstruct the three-dimensional structure of ionosphere based on measured signal of the integrated ionospheric parameter along the crossing signal path from the satellite to the receiver. So it can be mathematically explained by using this equation, which is y represent the vector of the observed slant TEC data. A is represent the geometry matrix, which is consists of the length ray path from the satellite to the receiver. X is the unknown vector, which is the electron density that will be estimated in this study. So the tomography, it actually consists of two main basic steps, which is the first one, tomography modeling, consists of the designing of the voxel size. And the second step is inversion technique or reconstruction method, which is involved with the inversion of the slant TEC to obtain the electron density for every voxels. So on the tomography modeling, it consists of, there are three main issues that need to be taken care, which is the first one, during the design, we need to focus on the coverage of the study area, where in the study, we are focused on the Peninsular Malaysia only, which is around 1 degree to 8 degree north and 99 degree east to 105 east. And the height interval and also size of the design voxels. So in this study, we propose using the size of the design voxels is 1 degree in latitude and 1 degree in longitude, with the height of interval is 50 kilometer in height, where it begins at the 100 kilometer to 1000 kilometer. And to simplify the understanding of the tomography modeling, it can be explained based on this diagram, where we can see the satellite passing through the design voxels to the receiver, where we can see the D here is actually represent the length of the ray traversed to the pixels. The X here is the electron density in the pixels. So while doing in this modeling, actually, we need to taking care of a few cases where the first case where the satellite passing through the design voxels at the center, how we would like to estimate the electron density. And the case two, where the ray path passing through at the bottom or the upper part of the design voxels. So in this, on the case 1 and the case 2, actually, we will assume that the electron density of the voxels is equal with the computed electron density value. And meanwhile, for the case 3, where there is no ray path passing through the design voxels. So in this case, actually, this will be, we will assume there are no electron, we cannot estimate the electron density in these voxels, which it will lead to the ill-conditioned matrices. Therefore, this part will be handled at the next step, which is the inversion technique or the reconstruction methods. Okay, in this step is inversion technique and reconstruction method. It lies in the inversion process because the occurrences of the inconsistency of the GPS observation and also the number of ray paths passing through the design voxel because of the satellite geometry, because there are no ray paths passing through. Therefore, we will need a proper technique or inversion technique or reconstruction method. So there are a number of the technique that I propose, which is we have the Fourier transformations method, and also we also have the algebraic reconstruction method. So in this study, we use the multiplicative algebraic reconstruction method, which is have been presented by Bender, in order to solve the ill-conditioned matrices that occurred during the tomography modeling. So the multiplicative algebraic reconstruction technique consists of 2 loops, which is inner loop and also the outer loop. For the inner loop, it involved with the processing of the observation and applied the correction to each voxels. And for the outer loop, involved with the next iteration until we found a suitable value of the approximations is obtained. And the iteration actually depends on the quality of the initial gaze, quality of the data, and also the other parameter. So for the initial gaze in this study, we use the Erie models as the background ionospheric, as the background value for during the reconstruction. So during the reconstruction, based on the design voxels, we will produce for 1 degree in latitude, in 1 degree in longitude, with the 50 kilometer in height, and the electron density profile will be produced for every 1 hour. So roughly this is the flowchart of the tomography module, where we input data will be involved with the GPS observation data, include together with the final orbit, we have the ionospheric model, ION, and also the satellite DCB. And then we will use the input to estimate the slant TEC estimation, where in this section, we will have the output, the slant TEC, and also the VTEC, and also the daily estimation of the receiver code bias by adopting the previous method that has been presented before. And then from there, we go to the tomography module, which is divided into 2 parts, which is the tomography modeling to determine the ray path passing through the design voxels, and also the reconstruction technique, where in here, we will use the additional input where we use the Erie 2012. And the output on this section is the electron density value. And the last part, and then we will map the 3D ionospheric profile. So we can see here at the right side is the yearly mean variations of the 3D ionospheric tomography from the year 2010 until 2012. So we'd like to highlight here the color scale bar here is different for every year, because we'd like to highlight to show the variations of the electron density profile. So the profile here shows that the ionosphere experienced the diurnal variation, which is increased increased together with the time of the day, which is also based on the rate of ionization, which is similar with the TEC trend that have been presented before. And then here also we compare with the TEC trend by monthly from the January to February, December from the year 2010 and 2012, where also exhibit the same trend of the TEC. And roughly from the result, we can see that the month-to-month TEC variations and the GPS tomography show the similar trends of increasing and decreasing of the ionosphere, where we can see also the March to May equinox show the higher variations of electron density compared to the October to November equinox. So further results and explanations analysis on this result, actually, all of you can refer to these 2 papers, which is the seasonal variations of equatorial anomaly crest using GPS ionospheric tomography, and also the reconstructions of 3-dimensional ionospheric profile by using the tomography technique. So further explanation can be referred to those papers. So on the last part is on the case study where we use the tomography to detect the equatorial plasma bubbles. So in here, we choose two case study, which is the first one has been presented by Sarudin on the upper part of the figure, which is on the 29th March 2011, where they shown in this rotikilogram that have been produced by Sarudin at cross sections of 5 degree north, where in their cross study, they shows at least there are 10 structure of the EPB. So in my study, actually, we focus on the red box here. So during the reconstruction, supposed to be we will able to detect at least 3 striations of the EPB. So during the on the night of the 29th March 2011, actually it has been reported with the minimum geomagnetic with the Kappa index around 0 to 2, and it is under the low solar activity. So when we do the reconstruction, we compute the rate of change electron density, and then we only observe based on the cross sections and the time given of the occurrences of the EPB compared with the ROTI. At least the tomography only able to detect only 1 striations of the EPB, which most likely represent the EPB5 that is represented here. And then for the next part is on the second case study is on Buhari 2014. On the 5th April 2011, at the cross sections of 4 degree north, we can see at this area, the at least 4 striations supposed to be tomography can be detected. However, in our study, we observed that only 2 striations, which is most likely represent EPB8 and EPB9. And then we also observed that there are difference in the time occurrences of the EPB, where ROTI actually occurs the EPB around 1250 UT. Meanwhile, the tomography is around 12 UT. Okay, this is because of the time gap of the reconstructions actually for every 1 hour. So where it only allowed the reconstructions of ionospheric tomography to detect only the stronger EPB, which is the large depletions can be detected. So on this part, actually, for the results, I also have represented in the paper detections of equatorial plasma bubble by using the GPS ionospheric tomography over Peninsular Malaysia. So for the analysis, results, and explanation also can be found in the study. And then, so roughly this is, and for the last one is on conclusions and recommendation. So we can conclude that this study proposed a technique and method for the reconstruction of electron density profile over the Peninsular Malaysia, where we found that where we generate 2D TEC to study the morphology of ionospheric variations over the study area, and we found that the variations of ionosphere exhibits annual, seasonal, and also diurnal variation. However, the 2D TEC only described on the ionosphere at the 400 kilometer only, where the reality of the variations of ionosphere depend on the condition of the top side and also bottom side of ionosphere as well. Therefore, the tomography technique has been proposed by using the GPS network over Peninsular Malaysia with voxel size 1 degree in latitude and longitude for horizontal resolution and 50 kilometer for vertical resolution with temporal variation for every 1 hour. And the MART technique has been applied in the module to overcome the ill-pose matrices during the inversion computations. And the result found that the ionospheric variations also exhibit the diurnals and seasonal variation as presented from the TEC result. So the case study also has been carried out with tomography method to capture the equatorial plasma bubble. And from the result, we can conclude that the GPS ionospheric tomography capable to overcome the limitations of the single layer model and obtain the vertical ionospheric information, where this method can be used to augment the classical technique, for example, the magnetometer and ionozone, and also to support the aviation, space weather studies, satellite communication, and GPS positioning, and for the development of the fundamental aspect in space weather studies and modeling the impact of the equatorial ionosphere in Malaysia. So from this study, a few recommendations has been suggested, where the first one is to reduce the GPS observational errors, where some of the slant TEC data should be removed, as suggested by Hong, where they only use 95% of the data from the median slant TEC data. Okay, this is because the data set of the slant TEC may have the value near to 0, and this could lead to the observational error. And then the second suggestion is time interval of the reconstruction should be reduced to 30 to 50 minutes in order to detect the small scale of ionospheric fluctuation or irregularities. However, the problem with this is we will need more processing time during the reconstruction. And the last suggestion is to do an integration of the GPS network and ionosphere station over the Southeast Asia, where it can cover the whole region and can act as the background model and improvement in ionospheric modeling over the region. And also, I would like to update some of the continuations of this study actually currently that what I'm working on. We try to develop a near real-time ionospheric tomography over the Southeast Asia region, where currently we encounter some of the problem actually where we want to have a background model and informations of the background model because we didn't have any informations of the real-time background models. So currently we are working on it to solve the issue, and hopefully that we can finish during the timeline. So that's all for today. So thank you.
Yeah, thank you so much, Syukriah. Very clear. Even though your slides very crowded. Only you could read it. Anyway, we follow what what you're saying. Then we invited our audience to talk to you, and I see that Professor Liu from Wuhan University. 那个吕老师你在吗？
Yes. Can you hear me?
Yeah, would you
Yes.
like to comment or
Oh yeah, I'm sorry. I was like 4 minutes late, but I caught up. Caught up in the motivation from the motivation. Yeah.
你可以把你的 camera 打开吗？你
Oh
so
yes, no problem.
So Professor Liu is from Wuhan University. I think she's working on a
Yes.
similar thing, and then so that I would like I mean I have also a couple of questions to Syukriah,
Yeah.
but you should have that too. But I think that the one thing that to have this working group is to, as Syukriah said very last in her conclusion, is that she's planning or she's working on a South Asia or Asian network, more or less to look at the events in a coordinated manner. Maybe since you're in Wuhan and she's in Malaysia, and maybe you could discuss that from that point of view. I mean, whether there's a possibility of building such a network. Yeah. I mean, this is a low latitude atmospheric physics, right? And because we are all at this region, I mean, not suffering, but experiencing this equatorial bubble event, and which is very important for space weather. And then I think this is a very rich field, you know, for people to look at. Yeah, please, Professor Liu.
Oh yeah, I have 2 questions regarding the technique part. Firstly, I see you only use the pseudo range for the modeling.
Yes.
Yeah,
Yes.
why not use like carry phase leveling pseudo range? I think that's a common method. No.
Yes.
Or
Okay.
maybe yeah. Maybe it's just the first experiment to have a try. In the future, you will use that, right?
Okay. Actually, during this is actually our first experiment by using the tomography.
I see.
So we would like to use the pseudo range because after that, when we are using the carrier phase, we also need to handle with the ambiguity resolution, right? Yeah. So there is the another part that we have to think about. So the first experience, actually, we would like to go on the pseudo range, and the future we will go on the carrier phase also.
And for the tomography part, yeah, it's different from the you focus on the regional tomography instead of the global. For the regional modeling, I think I have a question how to consider, for the low elevation satellite and one part of the ray it's beyond, it's out of the the modeling,
Yeah.
you know, this
Yes,
these
yes.
voxels. Yeah, how
Yes.
to remove it. I think it's the some part of the ionospheric delay should be removed,
Yes, correct.
or
Yes. So
by
during for this study actually we remove at least to remove what the problem for the low elevation satellite or during the outside of the reconstruction, we remove the observational data below than 20-degree elevations. So that's why we have only the high elevations data only.
Okay, I see. Yeah, I think that's one problem, you know,
Yes.
when we discuss this small region.
Yes.
Yeah.
Because before on the first during my first trial actually, during I did not remove the low elevation data, and then I encountered the problem during to obtain the optimal value of the electron density during the iterations, and then there is the problem that I have faced. And then after that, I go through on some of the other papers, and they suggested there are some suggestions that I've been considered on the first one where I implement in the study. Actually, I remove on the 20-degree data. And then there are also, just as I shown in the slide, actually, they propose that to remove the 95% of the slanty EC data.
Wow, I see. Okay. Yeah. Yeah, I see the plasma bubble part is quite interesting. Yeah.
Yes. Actually, that one is just the first experience which I tried to observe, and very fortunate that I able to see the detections of the plasma bubbles.
Great. I think that's very important for the equatorial region. Yeah, that's all. Thank you.
Thank you, Ron.
Any questions more from the audience? And I see that there's a Dr. Mohan Das. Do you have a question for Syukriah? Dr. Das? The one question I have to you, Syukriah, is that because I see the data you have been using from 2010 to 2012.
Yes.
You don't have any more recent data.
Actually, during the study period, actually, how I want to say this, the available data that we have is only during that period. Actually, during the study is only 2009 until 2014. The data that only we obtain. So since I've encountered a lot of problems during the reconstruction, actually, so during that time, the possible the reconstruction that I want to say during the limited time period, I only able to do for that 3 years. So because and then another thing is I observed that during that three consecutive years, actually during the ascending years of the solar cycle. So I think maybe it is one of the interesting part where I think I should consider why I used that during that period.
Okay, sounds reasonable. But on our hand, we're coming to the solar cycle 25, also the ascending lake. So it'll be very interesting for you, to have.
Actually, I'm working on that part actually. Yeah.
And because you are now using the basically the GPS satellite, right?
Yes,
and
yes.
You have you heard of this cosmic true measurements?
No. I just last 2 months I've been proposed by one of my friends. They suggested to use the cosmic. So right now I'm trying to looking on that part, but I did not have any experience using that data actually.
The data are all available in the public. I could I could connect you to the previous speaker, Dr. Chin Yang Lee.
Sure.
And he could show you, where to get the data. We
Yes,
have a comment, I think, from in the chat box. Isabella. Isabella, would you like to say just to speak out, Isabella? We cannot hear you yet. Isabella saying that it would be challenging finding solar cycle trends providing long time series.
Yes, correct. Actually, because I have if we want to go through on the for the time for a long time series, for example, if we go through for the one solar cycle, actually we can follow the trend. But if we want to focus on the segment, for example, for during 1 year like that, there are some. There are some trend because during year 2015, I observed that there are a difference of the solar cycles. The solar activities with the TEC trend, where I think that one is because of the geomagnetic activities that occurs. There are geomagnetic storm also occurs at early year 2015. Because the year 2015, we have the ascending phase of the solar cycles, but the TEC trend is a little bit, for my region, actually for the Malaysia region, we have the TEC trend is actually a little bit depleted like that. So that one may be because of the occurrences of the geomagnetic storm. So yes, I agree with the Isabella.
Yeah, thank you. I think you have the email address, Professor Liu, because you and her are also, and she are also the working group members.
Yes.
So you could write to her, and also Dr. Chiang Lin. You could also write to him. If you are interested in using the cosmic truth data. And, any other questions from the audience? I think there's some other comment. Let me see what's that. The Sadia said, did you find any time delays?
May I know what time delays is it?
Sadia, can you explain better?
Yeah, Prof. Can you hear me?
Can you open can you start your camera? Switch on your camera. It's okay. We cannot see you yet. If not, then just okay. Hello.
Hi.
You know each other?
I know.
No. Prof, I am currently working with this GPS TC analysis data. So we are trying to find out the geomagnetic storm index over Malaysia. So we have found some kind of time delays. Did you found any over your research period?
May I know time delays in which part?
So let me explain that Malaysia is situated in Equatorial region. So if geomagnetic storm occurs, in this part of Malaysia, in this Equatorial region, have some time delays. So we face some delays about 6 to 21 hours gap between the UTC time to the Malaysian time zone.
Did you mean the time delays of the geomagnetic storm occurrences?
Yeah.
Oh, okay. I have joined one of our research project actually. During the year 2015, on March, there is a one geomagnetic storm. During that time we detect the time delay is, I didn't remember the time, but there is a time delay during the detections with our Equatorial Ionospheric index system. We found that right after the geomagnetic storm has been reported, it is around two days or 3 days like that, if I'm not mistaken. Yeah, 2 days or 3 days like that. One of my friend already published the paper I think maybe you know, you can search for the paper near real-time Equatorial Ionosphere Index, or known as the EXA. Yes, there is a paper that have been reported by her.
Oh, one more question for you.
Yes.
That which software you use for these observations and
Oh,
calculations?
For the calculation, actually, I'm using the MATLAB software.
Mhm.
I'm fully using the MATLAB software, but for the using detections of the TEC trend, I'm using the Bernie software.
Bernie software. Yeah.
Bernie software, yes.
Okay. Thank you, Miss.
Thank you.
Uh,
Welcome.
Yeah, Professor Liu, you heard this conversation, right? Do you have any comment?
Actually, I do not know much about this. I understand it's like the ionosphere delayed response to the geomagnetic storm, right? You are discussing.
Yes,
Oh.
correct.
Yeah.
Okay. I have not paid much attention to that problem, which is quite interesting for me. Yeah.
Thank you.
Okay, great. Any other questions or comments to Syukriah? And either you raise your hand or just type on the chat box, and we read it to Syukriah. If not, and I think that the Syukriah, you have question, you know whom to write to, right? I mean, I hope that you would connect to them, you know, because it's
Yeah, sure.
very good to have a network, you know, to have experts working together. And then I hope that you all would join the next talk, and then look for possibility or opportunity to work together. And remember that I also want to mention that the AOGS annual meeting next year, this proposal deadline is the end of November. So if you are interested in writing a proposal, submit a proposal to coordinate, to convene a session, please do think about it. I will send information to the LLWG members, and Professor Liu, perhaps you'll be interested in writing a proposal, in submitting a proposal. Yeah, because the meeting will be held in Singapore.
Okay, I will think about the topic. I don't know which. Yeah.
I hope that this working group would together submit the proposal, and right.
Yes. Yeah. I think we can combine more stations, more networks. If we, to do some research. Yeah.
Okay, good. So that we are very happy, to have this seminar and have this discussions. And I thank you all. And I will end the session now. And thank you again. Hope to look forward to seeing you again. Thank you very much.
Thank you.
Yeah, bye-bye.
Bye-bye.
Thanks. Bye.
So we have some information on the chat box. Right. Okay, but I will send the announcement to you again. Yeah, thank you.
All right. Okay, thank you. Bye-bye.